Welcome to Spring LIB.
Okay, we've got a few different scenarios of charged particles in close proximity to each other, and we've got to figure out which of them have the highest potential energy. Right. So, what do we mean by potential energy? We mean the energy that would be released if we let the charged particles go. Right. Uh, so, yeah, this U is typically the symbol for potential energy. And the important thing is that we recognize that this potential energy is going to be proportional to, right? It's going to be proportional to the charges, right? So charge 1 times charge 2. And it's going to be inversely proportional to the distance between them. Where the distance is r, and that's squared. Okay. So if they're very close, right, then r shrinks and u grows. If they're very far away, then r grows and u shrinks. If the charges are very high, right, um, then they're going to be the potential energy is going to grow. And if the charges are very low, the potential energy will shrink. Right? So it's proportional to the charges, inversely proportional to the square of the distance between them. And the other thing we've got to consider is that if we have a positive and negative charge, right, those are going to be attractive. Those are going to fall in towards each other, right? Um, if instead we have positive charges, right, those are pushing away from each other. There's still potential energy, really. Right? So it's not going to make too big of a difference whether it's an attractive charge or not, right? Really, what we're dealing with here is the magnitude of the products of the charges and the distance between them. Right? Either way, we have potential energy. That potential energy is either a repulsion or it's an attraction. But in either case, if we let the particles fly, they would move, and they would move with because of some potential energy, and that potential energy at the end of the day would be proportional to the charges between them, as well as the distance between them. Right? So let's start jotting down our cases. Right. So first case is a charge of positive 2, next to a charge of negative 2, and the distance between them is 2 units. Right. Next case, we've got a charge of positive 4 and a charge of negative 1, and the distance between them is 1. Okay. Next, we've got a charge of positive 1 and a charge of negative 2, and the distance between them is 3. And finally, we've got a charge of positive 1 and a charge of positive 1, and the distance between them is 1, 2, 3, 4. Okay. So what we can do is basically just plug in the charges and the R and then see which of these 4 cases gives the biggest value, right? Units aren't super important. We just assume multiples of E or coulombs. It really doesn't matter. Um, yeah, right. We're not told distance units either, right? So the first case, right, we get 2 times 2 over 2 squared. And that looks like 4 over 4 or 1. Here we've got 1 times 2 over 3 squared, or 2/9. Okay. Over here we've got 4 times 1 divided by 1 squared. Looks like 4. And over here we've got 1 times 1 divided by 4 squared. That looks like 1/16. Right? So I'm going to use green to mark these highest to lowest. The highest number I see is 4, right? The next highest number I see is 1. The next highest number I see is 2/9, and the lowest number I see is 1/16. Right? So that's the order you'd want to mark them in. Counterclockwise, starting with the top right, 1, 2, 3, and 4.